Good afternoon, everybody. Welcome to Windows Vista kernel changes. My name is Mark Russinovich, and a lot of you probably know me from the SysInternals website. Some of the other roles that I have is as Chief Software Architect and co-founder of Winternals Software, and I'm also a co-author with Dave Solomon of the official Microsoft Press book on Windows XP Server 2003 internals. That's shown on the screen there, Windows internals.
Mark and I work together in our writing and also teaching Windows OS internals classes. We've also done some videos. You have a DVD in your bag for a new series that was just put up on SysInternals on Saturday. That's the first of a 6 DVD series, and you can read more information on the SysInternals homepage.
So this is an outline of what we're going to be covering. We've taken Vista kernel changes that we think are interesting and important for the evolution of Windows and divided them up into several categories, including process and threads, I/O and file system, memory management, startup and shutdown features, reliability and recovery enhancements, and finally we'll conclude with security.
Just wanted to get an idea of the audience, though, Mark. Is this, could you raise your hand if you're mainly, as Microsoft would call you, it's sort of an IT pro, IT interest? Raise your hand, IT pro. And dev, primarily dev. And keep your hands up if you're a dev doing what we would call system-level software, writing services, calling Windows API stuff. Hands up still. Okay, so we do have some in the room for that.
And you'll see throughout the slides references to APIs that apply to the particular area that the slide covers. Speaking of the scope of the talk, we're covering a large number of enhancements to the Windows Vista kernel. And when Dave and I sat down to prepare this talk and started to really dig in and take a look at what was going on in Vista.
Was that last night?
Earlier this morning. We were surprised at just how much has changed and how many improvements have gone to the OS.
Pleasantly surprised.
Pleasantly surprised. And actually, well, it was tight fitting it all into 75 minutes. And for that reason, we've chosen to limit the scope of the areas that we talk about. For example, we don't talk about a lot of the improvements that are in other major aspects of Vista, including networking, the graphics. We don't talk about Arrow. We're not going to talk about the window manager installation or management improvements. We're focusing on systems level, core operating system improvements. And incidentally, this talk could almost be called a Windows Server Longhorn internals talk, because everything we talk about today, the Vista OS will serve as the base OS for Windows Longhorn Server.
There are a few things that are going to be in Longhorn that are not in Vista today, but will be back in SP1 of Vista. So starting out with processes and threads, one low-level change in the time accounting mechanism of the system that really addresses something that has become more and more of a problem, and that is looking at CPU consumption for processes in the system has been, over time, becoming more and more useless. CPU times for most processes appear to be 0, as you can see here, or almost 0, because Windows kernel time accounting mechanisms are based on an interval clock timer beating at a rate of 10 or 15 milliseconds. And when that interval occurs, the system says, what's happening now? What's happening now? What's happening now? Which may not represent what happened in the last interval, especially as CPU speeds have gotten much faster. This also meant that time slices were not always applied fairly. For example, a thread might just begin running, as you see in the picture there. The clock fires, and its turn is over. Another thread gets a turn. Also, when interrupts occurred, the system was penalizing the thread that was interrupted by the driver and charging its time slice for the time the driver spent servicing the interrupt. This has now been addressed in Vista by utilizing a processor counter called a timestamp counter that allows Vista to query the number of cycles that have elapsed, and it now charges actual CPU cycles consumed by the threads. One of the things that Mark has added to Process Explorer is a column, the cycles delta, which reports the number of cycles that the threads in each process have consumed over the refresh interval, by default once a second. And what you can see very clearly here, in fact it's quite dramatic, in the CPU column there are very few entries that are non-zero, yet in the cycles delta column we can see there's lots of thread activity in processes that if you looked at Task Manager would show up as doing nothing. And that is because of that interval-based time accounting mechanism. This also means time slice accounting is more fair. Threads will at least get a turn when they start running, possibly a turn and a little bit extra. There are some APIs to query these numbers. That's what Mark's using in Process Explorer.
Another enhancement with respect to the way that the system uses CPU has to do with playing multimedia content like an audio or video clip. And if you've ever played such clips on previous versions of Windows and you've experienced the glitching that might occur, that's being addressed with a new service in Vista called the Multimedia Class Scheduler service. That service, applications that are playing content register with and declare their desire to have a glitch-free experience. The Multimedia Class Scheduler service then starts monitoring those threads and boosts their priorities up into the real-time range, far above the thread priorities of other threads in the system that are trying to consume CPU. And they can actually request up to 80% of the CPU. If they end up consuming all 80% of that CPU time that they've been granted, at the end of that interval, the Multimedia Class Scheduler takes their threads and slams them back down into an idle priority below the thread priorities of the other threads that want CPU, giving other activity a chance to execute.
And this is so easily seen in Vista. You run not even a super high priority thread in compute bound on XP, play music, the music stops. On Vista, it just keeps on playing. Something that I was excited to see come to the Vista kernel, because I'm coming from a VMS background from years ago. Any VMS fans in the room? Remember VMS? Slowly, NT's getting there. Hard resource quotas, per user resource quotas for not just memory, but also CPU. This is not something you're going to see documented yet. It's coming, but there will be a way to say for a given username, not a process, the kernel's going to maintain the potential to enforce hard resource quotas. And that's going to be of use for especially terminal server systems.
And for developers, there are a number of new synchronization APIs. Developers have in the past had to roll their own synchronization primitives to do things like reader-writer locks or condition variables. And Vista includes those now as a base part of the OS. In addition, a number of the core synchronization APIs have been fleshed out to better support the security needs of applications. For example, the create event API and the other synchronization creation APIs allow you to specify a desired access for the object that you're opening. Our next topic now is I/O and file systems, and we'll start by talking about something that Unix has had forever, but Windows users have been sorely missing, and that's symbolic file links. In Windows XP, Windows introduced the concept of a junction, which is a directory-based symbolic link. And now in Vista, they've extended that using the same underlying file system technology called a reparse point to support links between files. There's a tool built into Vista, actually, called MakeLink that lets you create both symbolic file links and symbolic directory links. And what I'm going to do is go to the root directory here and make a link between test.exe and notepad.exe. So I've just been told that the symbolic link was created. If I do a dir, it will actually, the command prompt actually is aware of these things and will show you that test.exe points over here to notepad.exe. And now if I run test.exe, we should see notepad appear on the screen. Now if I delete test.exe, what do you think is going to happen, Dave?
Will it delete notepad?
I don't know. Let's see. Notepad.
Oh, it's still there. It's just
okay,
really
I guess
amazing.
they got that case right.
Who in the room has used I/O completion ports in writing multi-threaded server apps? There's about 4 of you. But anyway, some work done in the way I/O completions are posted is going to have a non-trivial effect on I/O throughput improvements. In the current kernel, when a thread is pulling from an I/O completion port, the I/O completion had to be executed, the last part of it, in the context of the thread that issued the I/O, which caused unnecessary context switches and also delayed I/O completion because that thread might not wake up and run right away. In Vista, this last bit of work on an I/O completion is done when a thread wants to go process the I/O. And again, that just reduces the number of context switches.
Another enhancement related to I completion ports and asynchronous I/O in general is get queued completion status, where the API to pull an item off a completion port was done one item at a time. So if you had a thread that was pulling items off and could consume them very quickly, it had to keep going back to the kernel and pulling those things off. A lot of user mode to kernel mode transitions. With this new API, get queued completion status EX, you can actually specify that a number of completion statuses that you're willing to grab at one time. And the I/O system will try to satisfy as many of those as it can, allowing you to go into the kernel fewer times and improve the performance of your app. There's also a number of other APIs that are in this area that allow you to specify different kinds of behaviors for asynchronous I/O. For example, if you don't want a completion status for I/Os that don't end up completing successfully, for example. And these APIs are set file completion notification modes and set file I/O overlap range.
Now this one has a direct end user benefit. Prior to Vista, an open could not be canceled. I/Os could be canceled with the cancel I/O function. Now in Vista, there's a way to cancel an I/O with the new cancel synchronous I/O function. So that means if you're doing a net use or a net view, or let's do this example, I'm going to run Notepad and do a file save as and put //build g/foo. Uh-oh, that worked too fast. You know what? We're not connected to the network.
Right.
Sorry, we didn't plug in the LAN. If we were connected, that would have hung for a while. Familiar with that? And while it's sitting there hanging, trying to connect, you'll be able to press the cancel button. It's using that new cancel I/O, cancel synchronous I/O function.
So when we were talking about multimedia class scheduler and the enhancements to glitch-free audio multimedia experience, prior to Vista, you could have background activity that would interfere with your foreground activity, including things like playing audio or video, because prior to Vista, the only way to prioritize your work was based on the CPU, and it was missing a very important factor. And I think a lot of you, IT people and developers, realized that there was a kind of a glaring hole in the whole way that Windows handles prioritization.
And there's just a lot of other background stuff that we have to keep running now, like antivirus,
and now you've got defragmentation built into the OS.
content indexing
For all the search that goes on. So Windows Vista actually introduces the concept of prioritized I/O, and there's two types of prioritization that it takes into account. Prioritization of the individual I/O requests, as well as the ability for a thread to request a certain amount of I/O bandwidth from the device that it's interacting with. The I/O prioritization support in Vista requires the support of all the device drivers that are responsible for handling I/O. If they queue the I/Os, they need to honor the priorities and queue the high priorities I/Os ahead of the lower priority I/Os. And the core storage drivers in Windows that interact with storage disk devices and CD-ROMs and so on, the TAPI device and USB storage drivers, are where the core support for the system-level priority queues are implemented. SCSI support isn't going to be in the first release of Vista, but that will come later. The I/O priorities are based on the priority of the issuing thread, or by the thread explicitly setting an I/O priority on an individual I/O. And internally, Vista defines 5 levels, but only a few of them are currently implemented for this initial release of Vista. The I/O priorities are stored in the I/O request packet itself, and processes that know that there might be interfering with foreground work, like the indexing service or the Windows Defender scanning engine, can call new APIs like setPriorityClass and specify new flags that tell the I/O system the I/Os issued by this thread should be low priority I/Os and go behind the things that are normal priority I/Os, like your Outlook trying to read from the PST file. Bandwidth reservation is the other aspect of this, and this is where streaming applications get the benefit of the I/O prioritization. Something like Windows Media Player can request a bandwidth guarantee, and they do that by calling a new API called Get File Bandwidth Reservation, where they say, I'd like 80% of the bandwidth from this disk device so that I can play glitch-free video coming from a file. And the I/O system will return to it parameters that tell it how many I/Os it should be issuing per second and how many outstanding I/Os. In other words, how many I/Os it fires off before waiting for them to complete to try to get that bandwidth that it's targeting. So you can see down here in the bottom of the screen a picture of Windows Media Player that's requested some amount of bandwidth reservation. And as Windows Media Player is getting that bandwidth, then you've got it's consuming the reserved bandwidth. When it doesn't need I/O, that's when walk-in I/O can come in. So we call it reserving your spot and then walking in and just asking for it. So those walk-in I/Os then get to still be serviced, but while still preserving the bandwidth guarantees that the system has given to the consumer.
And in the other next click. Oh, I had Zoom is going.
Sorry.
Back, forward. Don't touch. There are these funny screens that are this funny blue color, apparently, that still occur. I haven't seen one in a long time, have you? Blue screen. Actually, most people never see them because Windows XP is defined to auto reboot after writing a mini dump, so it happens so fast they disappear. but apparently there are still some buggy drivers. The user mode driver framework provides a way for a class of drivers that are obviously not performance critical to the operation of the system, like you're not going to put your disk driver or the file system driver back in a user mode process. So for the kinds of devices listed on the bottom of the slide, there'll be an option to run their kernel mode driver in a user mode process, which means if the process crashes, it can be restarted without taking the system down. So if you look in the list of services, there is a new user mode driver framework service that will spawn off a child process for each user mode driver hosted in its own process so that if it messes up, it can't affect other user mode drivers, and will automatically restart them if they crash, and will take references to what, when they're running in kernel mode, or direct references to the OS, and map those down into the appropriate kernel mode reference to, in this case, the USB or FireWire driver.
Right, our next area is memory management enhancements, and we're going to start by talking about enhancement that applies or targeted at 32-bit systems, even though Vista, Microsoft plans on being the first 64-bit kind of focused operating system. They recognize that a lot of people are still going to be running 32-bit, and one of the behaviors of the memory manager prior to Vista was that at boot time, it would make certain decisions based on the amount of physical memory there was and whether your server or workstation and so on, and would carve up the address space that was reserved for the system, which by default is 2 gigabytes. So for example, it would give a small piece to the non-page pool virtual memory mappings, a piece to the page pool memory mappings, and carve up accordingly. What it could run into then are problems where one resource, one area of virtual memory would get exhausted, and it would have no way of then growing and taking away virtual memory from another area, like the non-page pool area, dynamically. So Vista addresses that by fully dynamicizing, is that a word? Dynamicizing the memory manager so that instead of coming up with these fixed regions that it defines at boot time, it's more flexible. And as the system's needs grow and shrink, it'll size page pool accordingly, non-page pool accordingly. And where you see a real benefit for this is in terminal server systems and for systems that have very memory Windows intensive. So you get a larger desktop heap, and you can support more concurrent terminal server users. Of course, that's not really applicable to the Vista client release, but like we said, this foundation is going into server, and it does influence a lot of scenarios even on a client OS. There's also there are various system virtual address space usage improvements. One of the most notable is the way that thread stacks in the kernel are handled. So a kernel mode thread stack, previously when thread became a GUI thread by issuing some GUI operation, it had to get a larger stack because GUI threads need larger stack space to store the call stack information as they execute GUI code. Then when they finished their executions, that larger stack would be fixed in memory and couldn't be reused for other things. In Windows Vista, the memory manager will take back that larger stack from the thread when it no longer needs it, and that makes the use of the system's virtual memory and the physical memory of the system even more efficient. Of course, none of this applies to 64-bit systems where, just like in Windows XP 64-bit, the memory manager will assign the largest regions that it can for the various regions of memory, like non-page pool and page pool, and there's no need to be dynamic about it.
And we'll never need more than that.
Right, 640K is enough for anything.
This next slide actually was painful to put together because it's hiding a huge amount of very low-level work in the memory manager that would take another hour to drill into. But if I had to summarize it, the work that was done in the memory manager beyond what Mark just described is all around reducing disk I/O. Disk has become more and more of a bottleneck in system performance as CPU speeds increase. So reducing the number of I/Os by making them larger, for example, read-aheads for cached files are now larger, so hopefully the data is going to be in RAM when it's referenced. Writes to the paging file are reduced because they are A, larger, or B, eliminated. In the case of writes that were containing entirely zeros, those are now eliminated. The next one is more towards server systems, but as multi-core becomes a desktop standard, better utilization of the CPU on MP boxes by improving concurrency. Support for the new Aero Glass video model, the next generation of DirectX. So these are just some of the things, and that last bullet, actually, which Mark's going to get into next, the support for superfetch, have a big overall effect on end-user system performance.
So in Windows XP, memory wasn't practically populated, meaning that the system didn't anticipate what you needed memory for. It didn't realize that every morning when you walk into the office, you open up Outlook and check your email. And so when you open up Outlook in that kind of condition, the system has to go on demand and fetch that stuff into memory. Windows XP did have a subsystem called the prefetcher, which did try to accelerate the boot process and application startup. But once you had an application up and running, if you switched away and did other things, you could end up taking memory away from that application. When you switch back, the application would then have to go and re-get all of the memory that it needed to in order to provide you an experience.
Or at lunch.
Or at lunch. You go off to lunch, you come back, you had Outlook running before lunch, other stuff happened while you were at lunch, background system activity took memory away from it, and then you open Outlook, and then there's a big delay as Outlook fetches its stuff back into memory. So the superfetch service that Dave referenced is actually, I consider it, and I think Dave you do too, a real breakthrough in virtual memory management. So there was, this is actually extremely significant in terms of giving users, or looking beyond just the simple application startup and looking across scenarios where you come back after lunch and the memory manager anticipates that you're going to run Outlook, has those pages already in memory, so when Outlook does open up, it doesn't have to go fetch from disk. It actually monitors the things you do, and it monitors on a daily basis, on an hourly basis, even on a weekly basis. So if you run a particular app once a week, every Saturday morning between 8 and 10, the system starts to learn that and will have the pages of that application in memory ready to go when you launch it.
Now, Superfetch is some work in the kernel and also some work in a new service that you'd see running in an SVC host. The kernel is now keeping usage information that this service can query in order to create these scenario files, and then to call the kernel to pre-populate memory with, as Mark said, the things that it knows, or at least it thinks that you're going to be referencing the most. And the other thing that the superfetch mechanism does that the current XP prefetch mechanism doesn't do is keep in memory private virtual memory in use by a process that you've had up. The XP prefetch mechanism brought in initially when you started an app pieces of code or other memory map files that were referenced, but not the private memory in the process address space that was used after the process had started.
So as another support feature for improving the performance of the system, Vista introduces something called ReadyBoost, where the memory manager will store read-only pages on an external non-volatile memory, like that memory stick right there.
Let's see how hard this is to do.
Here. So I've just inserted the key, and we should see pop-up here. There we go. And so that pop-up tells us that it gives us the option to speed up our system. What it's really asking us is if we'd like to put a prioritized page file, temporary page file on that device that mirrors some of the data, the most important data, the most relevant data that is actually stored on the real paging file. And what that means is when the system goes to read a page that's not present in physical memory, it'll first check the device's paging file before then falling back on the much slower disk paging file. And so it's a prioritized page cache, and Superfetch is integrated with this, of course, in order to aid the prioritization of pages and give you the quick access to those pages that it thinks you're going to need right away.
So you can have one of these per system. There is a minimum size listed there. It's a minimum speed. So it does actually do a speed test when you insert it, and if it doesn't meet that criteria, it doesn't give you the option to use it for ReadyBoost. Related to non-volatile cache is the upcoming release of hard drives that have non-volatile RAM as part of the drive. It's Samsung and, where's Matt? Samsung and Seagate have announced drives that are going to be shipping in mobile systems at the time that Vista is released. Is that this century, right? No, real soon now. It's worth waiting for, folks. And these hybrid hard drives then are populated by the Vista kernel support for Superfetch to contain the kind of stuff that would be put on one of these ReadyBoost USB keys, so that hard drive access is reduced, going to the non-volatile RAM, not only for Superfetch data, but also for boot time prefetch data, and when putting the system into a sleep state, part of the hibernate file. So this is going to improve battery utilization. When a laptop's on battery, part of this non-volatile RAM is going to be used as a write cache, so that reads from data written to disk will be coming back from this non-volatile RAM. We didn't do justice to Superfetch, Ready Drive, and ReadyBoost, but there will be a session on Wednesday, you can see in the bottom of the slide, entirely dedicated to these three topics. So we encourage you to go. Some very cool demos that you're going to see on what a difference Superfetch makes. That's session CL312 Wednesday, morning.
Our next topic is startup and shutdown, and we'll start by talking about visible change if you've ever messed with the great Bootini. In other words, the boot.ini file, where you go and add options or add different OSs to the system. The boot.ini file is gone in Windows Vista. If you've gone looking for it, you're not going to find it, and that's because there's a new boot mechanism that's been defined for Vista that abstracts different boot architectures, including EFI, Extensible Firmware Interface, and the BIOS boot architecture of current PCs under a single umbrella called the Boot Configuration Database. So the goal of this is to unify across the different OS installations as well. The same boot files are used to boot whether you're booting from a single installation or side-by-side installation of Windows. Finally, Unicode string support's present, so now the interface presented to users during the boot process can be internationalized. This boot configuration database is actually stored in the registry. And if we pull up the registry editor,
Mark.
oh, what's that? Oh, we'll talk about that later.
Okay. We just love the extra mouse clicks.
The boot configuration database is stored here in the registry, but unfortunately it's not like you can come and go and mess with this and edit it the way that you used to just open a notepad file and mess with boot.ini. I'm going to search, for example, WinLoad, which is the new operating system loader, and you'll see that there's a reference to the WinLoad executable here as something called an element inside this elements subkey, and there's many different subkeys under some key that has a GUID name. So this is all opaque, little blobs of data that the boot configuration database manager knows how to interpret. You can actually find that database on disk if we go navigate to the boot drive on this, or the system volume, sorry, on this system, according to Microsoft terminology. Here's the, where is it? It's in here in boot. BCD is the registry hive that we were just looking at that's been loaded in the registry. You can see it's separate from the Windows installation under this boot directory that would be used and shared whether you had the single installation of Vista or multiple installations of Vista on the same machine. Internally, the blobs that we just saw are configured in this hierarchical storage where the BCD system store is the kind of the root of the boot configuration database, and then hanging off it are the boot manager, the core boot guidance for the computer. So this is where you'd specify your boot menu timeout, your default boot selection, your display order, the kinds of things that you are used to putting in boot.ini. And then for each boot installation, you would specify the path to the bootloader for that operating system installation, along with the settings that are applied to that operating system installation. So for example, the NX settings or the PAE settings would be associated with a particular installation of Vista or a particular boot configuration entry. And there's also still support for legacy Windows operating systems and other operating systems. So if you had side-by-side Windows XP and Windows Vista booting, you would have a legacy bootloader specified over there on the right side in the boot configuration database. The utility that Microsoft ships with Vista to mess with the boot configuration database is something called BCD Edit, which, if you've ever played with it, is not the most friendly interface in the world. I'm just going to show you the output of it. And you can see that on this system, the boot manager settings are shown at the top, and the bootloader for the single Vista installation we have here is shown on the bottom. If you want to actually edit things, there's a kind of obtuse syntax you've got to use, and it usually requires more than one command to make a setting change. Microsoft, though, has documented the interfaces to manipulating the boot configuration database as WMI APIs. And they expect that if you really don't like BCD Edit, well, go roll your own.
Now let's look a little further at the new files involved in getting Windows to boot. Currently, when you boot XP or Server 2003, the boot sector loads a file called ntloader, which then opens boot.ini. So that half of ntloader has been replaced by a file that is in the root of the system volume where the boot files are, called bootmgr. So that's a half of what ntldr used to do in XP in 2003. So bootmgr reads the boot configuration database, presents the choices, and then passes control, if you're booting Vista, to a new OS-specific image called winload.exe That lives in the Windows System 32 directory. And on 64-bit Windows, it lives in the,
Syswell 64.
nope,
What?
Windows System 32.
Oh.
64-bit Windows, 64-bit files are in Windows System 32, of course. And that's the file that would load the OS image, entouskernel.exe, the boot drivers, the system registry hive, and pass control to the OS. So there's one WinLoad per OS installation, one boot MGR per system volume, which on this laptop is D. In the boot manager can also run other executables like WinResume is what implements resuming from Hibernate. That was also previously code that was inside NTLDR. And there's also now, out of the box, waiting for you to run the new Windows Memory Diagnostic, which is something that's been available, but you had to go download and install. And that's in this boot folder. There it is, memtest.exe.
So there have been some enhancements to the way that the boot process works once Windows starts getting up and running. One of them is that the session manager process, SMSS, created WinLogon and CSRSS for each session that you had on the machine. And this really impacted you if you had a terminal server system because it was a bottleneck for having multiple users log in at the same time. Session Manager had to go and create these processes for each user logging in serially. WinLogon, the interactive login manager, was created by the local security authority and the service control manager. So there was a kind of a weird mix of roles for these different processes. What's WinLogon, the interactive login manager, doing creating the authentication process? So in Windows Vista, there's been some re-architecture, where now there's an initial session manager process that creates an instance of itself to initialize each session as needed. And then that secondary SMSS exits. So if we scroll up in Process Explorer and find the initial SMSS here,
Session 0.
Session 0, it's spawned off WinInit, which is then the parent of services.exe and the local security authority subsystem down here, as well as a local session manager, which is a new process in Windows Vista whose responsibility is managing the terminal server state for that particular session. So they've broken that out and now into a separate process. Now it's already also created CSRSS here. And the secondary SMSS here, because you can see if you look at the session column now, the applications we're running are in session 1. These processes like WinLogon have no parent. If we go to the image tab, you'll see that the parent is a non-existent process. And that's because the parent of this process was that secondary SMSS that the primary one created to start this particular session. After that secondary SMSS created WinLogon and CSRSS for this session, it exited.
Now on a terminal server, that means 100 people who sign in at the same time can all get their sessions starting up at the same time. Well, we're talking about Vista. This actually applies to Vista. Anybody use Media Center Edition of XP? Do you have any Media Center extenders where you can watch your Media Center from other TVs? Now, if 4 people in the house at the same time turn on their media extender, their sessions can initialize in parallel, and they can be watching TV much sooner. There was another reason for the separation that Mark just showed about the console user being in session 1, and that is for security reasons. The namespace that processes shared in XP and earlier for the console user raised the issue of name collisions, a global name for some synchronization object that a Windows System Service process created that could also be referenced and or perhaps hijacked by some other process that the interactive console user would run. And because most of us ran as admin, that did cause potential namespace collisions. Also, services that, although they shouldn't have, presented Windows on the console could open the door to elevation attacks because the console user may not be someone that should be talking to that service process. So in Vista, the console user is not in session 0, as they are in XP, but they're in a new session. Now on XP Home, the second user to log in is session 1. On Vista, the first user to log in is session 1, and the second is session 2. And that keeps the namespace and the Windows message connection separated.
So you might have noticed something else in the process tree when we were browsing around there in Process Explorer, and that's that WinLogon has a child here called logonui.exe. And this is part of the new interactive logon architecture that's being introduced in Windows Vista, because prior to Vista, if you wanted to provide an alternate way of asking for credentials that was differed from the standard way of asking for a password, you had to write something called a graphical identification and authentication DLL, or a GINA. The problem with writing a GINA, besides the fact that the documentation was a little bit weak, to put it pleasantly, was that it was extremely complicated to write one, or it was simply hard to write one. Further, and most importantly, you could only have one GINA loaded on the system at any given point in time. So you'd either pick, well, I want the smart card GINA, or the password GINA, or the biometric GINA. In Windows Vista, this new logon architecture allows you to have what are called credential providers that each have their own way or their own mechanisms of asking for the user's credentials. And you can have more than one of these loaded at any point in time. They're much easier to write. There's a COM interface between the COM style interface between the logon UI and the credential providers. And the end user is given the opportunity to select interactively, if they want to, which credential provider they want to use. If they want to provide a smart card, they can. If they want to provide a password, they can. In fact, in Windows Vista, there's two credential providers that ship in the box, the password and the smart card providers, and we can find those providers in the DLL, the loaded DLL list of Logon UI by scrolling down. And here's the Windows shell user logon. This is the password credential provider mapped into the Logon UI, and down here, just a couple entries below it, you see the smart card provider, credential provider, mapped in it at the same time. So if there was a smart card present, the smart card provider, or a smart card reader present, the smart card provider would know to pop up a UI. And speaking of UI, Windows Vista doesn't let the credential provider go and completely replace the UI. It lets it augment the UI that's presented to the user, and it does it with this kind of flexible interface where the Logon UI manager will say, okay, credential provider, you want to give the user an opportunity to provide credentials? Tell me what you need me to display for you. And they'll say, well, I need an edit box, or I need a little block of static text, and here's what it should say, and I want you to give me a button. And the Logon UI manager will go and craft the UI dynamically for it.
Also, one other thing is because this code is now not running in WinLogon, you all know what happens to your system when WinLogon exits blue screen. This is going to crash a process that is not going to cause the system to crash. When we boot, now, of course, we never reboot, right? There's no reason to reboot. You ever rebooted? I haven't rebooted since 1993.
Well, every first Tuesday of every month I do.
Okay. Well, other than the security fixes, we don't reboot. There are a number of services that Windows needs to start, but aren't critical to the boot process. So now there's a new attribute of a service called delayed auto start. If a service is marked delayed auto start, these services are started after the normal automatic start services. And they're also, when they're starting, set their thread, the thread inside the service hosting process, is set to a low priority during the initialization of the service. It's then returned back to the normal priority. There's a few services out of the box configured that way. For example, Bits, Windows Update Client. And this is going to give, again, the feeling that the system is up and usable faster. You'll be able to log in and get going while this stuff is still starting up at a low priority.
So prior to Windows Vista, the way that shutdown worked on Windows was that the system would give the Windows services a certain amount of time to shut down. And that the amount of time actually was defaulted to 20 seconds and was specified in the registry. And what that meant is that the CSRSS process, as part of the shutdown, would tell the service control manager, hey, it's time to clean up. The service control manager then would go and inform the services that cared that it was time to get ready for the system shutdown. CSRSS, though, would go ahead and shut down the system after that timeout, regardless of whether or not the service control manager had told it that the services had exited. And that basically meant that you could have the rug pulled out from underneath you if you're a Windows service. That's one of the reasons that on large server systems, you're told to go and increase that default value, for example, on an Exchange server to some larger number to give those services a chance to flush all their data to disk during the shutdown.
But you never know, in fact, if they had enough time to do that.
You really don't. There was no notification that, hey, this service got the rug pulled out, yanked from beneath them. So you knew to increase that timeout. Well, in Windows Vista, now services are expected to be responsible. Those that use a new API that allows them to extend the shutdown time period for them, they can request a pre-shutdown notification. And that means that the service control manager will go and notify them before the other services that the system is going down. Then they can indefinitely postpone the shutdown. CSRSS will effectively wait forever for these guys to shut down if they need that time to shut down by just telling the system that they're still busy. And after all the pre-shutdown services have stopped, then it proceeds with the normal legacy style shutdown where the rest of the services are given at most the default 20 seconds to get their act together. So I guess this is another way to make your system hang at the shutdown.
Yeah, it's just a new way. No, it's important for reliability. There is a way also for the services that are shutting down to specify their shutdown order, just like services can on their startup to specify dependencies, group names, and tags. There's a reg key mentioned under the pre-shutdown order value. It's a list of multi-strings that services can put themselves in so that the service control manager knows in what order services should be shut down. And there's a couple of examples, actually just two in there right now. The Windows Update Service and the Group Policy Service have the shutdown ordering specified. One other thing related to shutdown is standby hibernate. I don't know about you, but as a laptop user, I stand by. I used to be a hibernate guy, and now I'm a standby guy. And of course, in Vista, if you go and look at the power button, it says, keep your session in memory and puts the computer in a low power state. That's standby. On desktops, that's going to do a standby and hibernate, something that you might have heard referred to as hybrid sleep. There are still the separate standby and hibernate, now called sleep and hibernate, available on that little side arrow. But one of the problems in XP is that if a driver or an app didn't want to allow the system to go into standby hibernate, it could say, no, we're not going to do that. And the system would say, oh, well, you've closed your laptop, put it in your bag, and meanwhile the laptop is on. That's happened to me. Raise your hand if it's happened to you. That's not going to happen anymore. Now you can close your laptop and be confident that the system is going to be quickly in a standby or hibernate state, whatever you chose. And drivers won't be able to veto this sleep transition. So that's really a nice improvement for mobile users.
Okay, let's move on to talking about reliability and recovery features. We're going to start with, I think, one of the coolest under-the-hood features in Vista. That's, well, I'll show you how it's exposed to IT developers. It's not really exposed as an end-user feature that your mom would think is interesting. But the kernel transaction manager is there to ease the life, ease the burden, and make it much easier to write reliable applications. Back before this service existed, if you were a developer and you were responding to some kind of client request or some kind of operation that required changes to multiple data sources, like you had to go and update a file, and you had to update a register key, and then you maybe had to go update some kind of database, you had to worry about the possibility, or at least you should have, of error occurring anywhere during those steps. And if an error occurred, be able to undo everything you'd done. Further, you had to synchronize access to that state that was being changed between other people trying to look at it, so that they would either see that state before the change or after the change and not see some kind of intermediate weird mix of things that reflect before and after. It was very complicated. It's very complicated to write that kind of support into an application. So when the kernel transaction manager implements a general transaction facility that provides all or nothing transaction semantics, the changes are only committed and viewable by other threads in the system once the associated transaction commits, and it's extensible through third-party resource managers. Built into the Vista operating system are registry and NTFS providers that work with the transaction manager. And they rely on the common log file system, clfs.sys, which was actually introduced in Server 2003 in order to provide fast temporary storage for saving the state of stuff that's changed as part of a transaction but hasn't been committed yet and then would be deleted out of the log file system. Like I said, third parties can write user mode or kernel mode resource managers as well to plug right into this, and that would be like a database manager that would want to plug in to the transactions.
Now, the usage of these things from the programming point of view is as simple as adding a create transaction, or a create transaction, a start a transaction. Now, everything done by that thread that is being handled by something that's integrated with the kernel transaction manager is going to get transaction journals so that if until the transaction is committed, the changes don't appear, and if the thread exited or the process died for some reason, the system would do an automatic rollback. But it's even easier than that from the command line. Mark, why don't you show us the new transaction command?
So we've got a command prompt here.
There you go.
Oh, okay, here it is. And the command prompt in Windows Vista includes a new API called transaction. You specify create flag, and that will start a new transaction for this thread and for any descendants of this thread. Oh, start, sorry. Start. So I've just created a new transaction. It's got a transaction ID that's a GUID that we can see there. And now everything that I do in this command prompt is being managed through the transaction manager. Watch, I'll make a directory, make dir new, and there it is, empty directory. Now I'm going to launch regedit.
Oh, you had it up already. You need to
I had it.
and restart
it. So this regedit is now a child of that thread that's in the transaction. I'm going to go to the top level key here and create a new subkey called test. Well, some problem there. There it is, new key.
It's a great name, though.
It's a great name. Yeah, I really wanted that name. Now I'm going to exit the registry editor. I'm going to come back, and I'm going to cancel that transaction by specifying the rollback flag.
Unbelievable.
And the directory's gone. Let's launch
Mind-boggling.
regedit again and navigate over to software. And that new key is gone. And so that transaction command in the command prompt is there for people that want to write scripts that rely on transactions.
I don't know if I can go on.
It is.
You go on.
Okay. I'll take over. So one of the really cool features in Windows XP that was kind of underneath the hood was something called volume shadow copy, where volume shadow copy would let you make instantaneous point-in-time views of a volume. And that was especially useful for situations where you wanted to do backups of volumes. It got around this open file backup problem where files could be locked and then the backup application wouldn't be able to open them, because the backup application would actually back up the files off the snapshot. And no application has files open on this point-in-time version of that volume.
I think that was a very undersold feature in XP.
It was an extremely undersold feature. Well, it wasn't really exposed, only through the backup application.
But in XP, if you start a backup, while it's running, you go delete files, create files. Those files that you delete will be in the backup, but the files that you create won't be, because it's reading from a point-in-time snapshot.
Well, in Windows Server 2003, Microsoft took that volume shadow copy feature and actually exposed it to end users through something called shadow copies for shared folders. And if on a Server 2003 system, systems administrator could go to the volume properties for a volume and specify that they wanted snapshots created at some interval for that volume. If they had end users then that map shares off of that volume, those end users would see in their Explorer Properties dialog box.
If they install the special extension.
Well, it was actually shipped with XPSP2.
Oh, sorry.
They would see a previous versions tab that would let them look at the contents of their files and folders in those previous snapshots. Well, in Windows Vista, they've decided to take the volume shadow copy feature further and integrate that into the OS, expose that previous versions tab for the local user of their own volumes. And not only that, they realized, well, Windows XP had this feature called System Restore, which would monitor for changes to system files and then store those in subdirectories associated with a particular point-in-time System Restore point. So that instead of having System Restore doing the monitoring and protection of the system files and have volume shadow copy going on at the same time, they decided to just re-implement System Restore to leverage the same volume shadow copy functionality. So now the same point-in-time snapshots that end users use to get access to their previous files and folders are also used by System Restore to get access to the system state as it existed at a previous point in time.
Now we have a snapshot. Actually, we can show this if I bring up Explorer, go to the C drive, look under Program Files. We installed earlier this afternoon the PowerPoint viewer so that we could show you this presentation. This was a clean Vista Beta 2 installation. By the way, we're running Vista Beta 2 up here on this laptop. I'm going to go back up to the root of the C drive and do a right-click Properties on the Program Files folder. And sure enough, there's a previous version. From earlier today, yes, the clock was wrong, at 11:32 this morning, a snapshot was made, and notice the Microsoft Office folder is not there. So we're looking at that folder, again, using the snapshot that's sitting there that was taken that did not have the presence of the Microsoft Office folder.
And those snapshots are by default taken once per day, and also whenever you in Windows XP had a scenario that caused the creation of a System Restore point, you also get a snapshot taken then, like the installation of an unsigned driver or the installation of an application that integrates with the System Restore functionality.
Now, In XP and Server 2003, there were cases where if a thread was running and due to a pointer bug had its stack corrupted to the point where the exception dispatching code could not walk the stack, an exception in a process like an access violation could go unreportable. The so-called disappearing process. Who's ever had a process, the window just disappears, no, we're sorry, no, Dr. Watson. That's fixed in Vista. And that's because in the kernel, unhandled exceptions are now sent to a new port listened to by a new service called the Windows Error Reporting Service running that launches the fault reporting out of process. So in XP and Server 2003, the code that launched the post-mortem activity was executed in the context of the process that was keeling over and dying, thus relying on its state to be in a reasonably valid state, thread stacks in particular. And in Vista, that now happens out of process. Simple demo, here's a little applet Mark wrote that's got a serious bug, one of your, as opposed to the other bugs that you have in your other tools. Running this applet on XP, when you click the trash stack button, causes the message box to disappear because the stack is trashed to the point where the exception can't be dispatched. On Vista, we get the beautiful new Vista error reporting dialog, and it's checking back.
Is that a progress dialog? Is that a progress bar?
And there is no solution, Mark. They're working on it. But at least there's some UI to the user that the process did have a crash. This next slide is also one where it could be another hour and 15 minutes. And in fact, there is a session I want to point you to. It's not on the slide, but tomorrow at 2:45 p.m., building reliability into Windows Vista is going to drill into some of the reliability extensions in the kernel. And that was one of the things that Mark said was a little bit outside the scope of the talk. But just to pick a couple of things that are worth noting, there are some new Windows APIs that allow debuggers to go report back a case that is very difficult or impossible to debug, and that's deadlocks, especially across processes. One thread waiting on a mutex, another thread waiting on a mutex owned by the first thread, it's a deadlock. These APIs allow a debugger now to go query that deadlock state and report it back to the developer. Something called the Restart Manager is some infrastructure that allows apps to declare themselves and the system files they're using so that when a service needs to be restarted, they can be informed so that DLLs can be unloaded, thus allowing a number of the core services that were not restartable in XP in 2003 to be able to be restarted without requiring a reboot. And there's a reference to a Windows API that points to others that show how apps can tie into that Restart Manager mechanism. And the last bullet on there refers to one of several new uses of the event trace mechanism that's been in the Windows kernel since Windows 2000, but extended quite a bit in Vista, called the Circular Kernel Context Logger, which is kind of like a black box flight data recorder. So as the system is running, it's keeping a detailed record of the last N events that can be used when things go wrong, either I/O-related errors,
application problems,
deadlocks, to be able to go initiate some kind of recovery. Again, there's more to say here. We point you to the session Tuesday, 2:45, building reliability into Windows Vista. A lot of work being done to add self-diagnosis and also auto-repair. For example, the system startup repair tool, which now when you boot an unbootable system will go through a number of checks to fix the most common causes for unbooting Windows systems.
So our final topic is security. We've got a bunch of features in here, starting with something called BitLocker. BitLocker addresses a vulnerability that Windows laptop users have long suffered with, and that's that you take your laptop on the road, and unless you've taken steps to encrypt your individual sensitive documents, your laptop gets stolen and somebody gets access to them. What's even worse is that the cached credential verifiers of your cached domain logons are stored in the local system on the hard disk. And about a year ago, somebody wrote and opened a program called Cache Dump, complete with source code that would reach into the system, pull out those cached verifiers, and extract them in a form that was easy to pass to an open source password cracker, John the Ripper. So you're walking around with your laptop and all of your sensitive information, even those encrypted files, could potentially be compromised if somebody can crack those passwords that are protecting them. But in Windows Vista, BitLocker makes it possible for you to very easily and transparently encrypt your entire operating system volume, the volume that's called the boot volume. The BitLocker feature isn't going to be present on all platforms, though, you need certain types of operating hardware support in order for BitLocker to function. For example, you need a trusted platform module, TPM version 1.2 or higher, or a USB-capable device and a USB device and a USB-capable BIOS. You also need 2 volumes. So this is where you need to split the system volume and the boot volume into 2 separate partitions. And that's the way you saw this machine's configured, because it's BitLocker ready. That second volume, the unencrypted one that the system actually boots from, where the boot files are stored, has to be 1.5 gigabytes in size at this time. And you're probably saying, why does it have to be so big? The answer comes from the way that setup's architected. And setup, as of beta 2, will be fooled if the volume's a little bit smaller than that into doing the wrong thing. So 1.5 gig is kind of a temporary thing, and that might change in the future. But it deals with the setup architecture the way that's currently implemented. There are several supported modes for storing the decryption keys. So there's a key that's used to encrypt the data on the volume, and the system then secures the key that's used to decrypt the data off of that disk. Depending on the hardware that you've got and the way that you want to use BitLocker, you get a choice of sealing the key inside of the trusted platform module. And the trusted platform module, the sealing, you can say, is transparent, so that when you boot the machine, you don't have to type anything in. It's just the system decrypts the volume as it runs and encrypts the data as it goes back out. And the way that it can ensure that the key is securely inside of the TPM is by sealing it with the hash or the signatures of the files involved with the boot process, starting with the master boot record. And the BIOS is the root of that trust chain. The BIOS is given a signature for what the master boot record should look like, and then it goes and verifies that it looks that way before it actually calls into the MBR code to kick off the first part of the boot. And then the MBR then checks the signature on the boot manager that Dave pointed out, or the boot sector, and then the boot sector then checks the boot manager file, and the boot manager then checks the WinLoader, and so on. And you've got this train of trust, so that somebody can't just move the disk to a different machine. Somebody can't insert something in the boot process that could compromise the access to that volume. Somebody can't do a side-by-side installation and then gain access to the machine. But there are other mechanisms. If you don't have a TPM or you want an extra layer of security, you can actually specify that you want to give it a PIN during the early part of the boot process. Or if you don't have a TPM, store the decryption key on an external USB device. And the mode of operation Microsoft anticipates here is that you've got a USB flash with the key on it. You put your key on it, because what they don't want you doing is sticking the key in your laptop and then leaving it in the laptop and walking away, because somebody then gains access to your encrypted files. They want it so that they recommend that you put it someplace where you're going to want to pull that key out because it's got other stuff on it. The components involved with implementing BitLocker internally are a driver that gives Vista access to the trusted platform module interfaces, and a filter driver, called a volume filter driver, that lives between the file system drivers and the actual volume that's being encrypted, called fvevol.sys. This is at the same level, by the way, that the shadow copy driver that we talked about earlier lives. And as NTFS writes data down to the disk, fvevol intercepts it and then decrypts it on its way down. The same thing correspondingly on the way up. It decrypts the data, and you'll never even know that's going on. Now, another feature in Windows Vista is aimed at keeping out bad code, and that's something called code integrity verification. The operating system loader and the kernel perform code signature checks. They check to see that if the images are signed by somebody trusted by Microsoft. And on 64-bit platforms for x64, they actually go a step further. They want to keep people from writing kernel mode rootkits. And as part of that, all kernel mode code must be signed indirectly by Microsoft. And the way that this works is that somebody that's writing kernel mode drivers submits a certificate from one of 3 certificate authorities that Microsoft has recognized as being responsible. Microsoft will then sign that certificate and give it back, and then the user embeds signatures inside of the driver file so that the system can check for them as the system boots. On 32-bit platforms, it's not quite as stringent, because there's still a lot of 32-bit kernel mode code out there. Microsoft doesn't want to break backward compatibility in scenarios where people are upgrading from XP to Vista. So the administrators are prompted to install and accept unsigned kernel mode code at the time of installation. And load time checks are still performed to see if they've got signatures, because you won't be able to watch high definition video content if you've got an untrusted kernel mode driver. What Microsoft wants to guarantee the media providers, the content providers, is that somebody's not going to be able to easily hack the digital rights management protection keys that are protecting that high definition content. If you had a kernel mode driver that you didn't trust on the system, they wouldn't be able to make that kind of guarantee.
And that ties in exactly to protected processes. Protected processes is a new mechanism in Windows Vista that at the moment is only usable through the new Media Foundation services. The protected media path APIs allow a process to be created as a protected process, and this is part of the digital rights management support to secure high-def content. There actually is a protected process on your typical out-of-the-box Vista system. It's the audio DG process, which is a child of a service living inside this SPC host that runs a part of the Windows audio infrastructure. And if we look inside or at the properties of audio DG, we're not able to look at any of the performance counters. We're not able to change the state of threads, for example, suspend or kill one of the threads in that process. We can just query limited information. So this is being mentioned now even for code such as debuggers or other system display tools that now may be getting access denied errors on processes that they normally would have access to. So even if you have the debug privilege, which on XP in 2003 and Vista gives you unlimited access to a process even if you have no rights to that process, that doesn't apply to secure or protected processes. You have a limited query capability and the ability to change a couple of limited attributes like the affinity and I think the priority of the process.
So one of the problems with buffer overflow exploits that Windows has faced is that it makes it it used to in the past make it relatively easy for somebody to write an exploit and then cause some function, some system function to execute that would allow the worm to install itself and embed itself on the machine. And the way that it made that easy is that DLLs, system DLLs, would always load at the same places in memory across the same version of the operating system. So the hacker could look and see, well, this particular function is always going to be at this address, so I'm going to craft my worm to go and try to execute the code at that address. Microsoft announced this actually within the last 2 weeks, something called address-based load randomization, or ASLR, where Windows Vista will move system executables and system DLLs around in memory to and base them at one of 256 random spots. So now a hacker can't just blindly go and execute some address because the function that they're looking for won't necessarily be there. And you might be thinking, well, 256, they got 256 opportunities. Typically in a buffer overflow exploit, they've got a very tiny piece of code that they can get to execute, and it's not like they can go fishing for these addresses. And if they miss, they're probably going to crash the process that they've infected. Also, the stacks are also randomized, so they can't even try to rely on stack locations that they might have previously relied on as having certain addresses for layout of variables and other buffers inside of a process they infect.
So these randomizations occur not on each process start, but at system startup.
The randomizations they base it at system start. So if you user32.dll, which is mapped into many processes address space, the system says, well, I'm going to base it at this random location, and then all of the other processes then use that same user32 mapped into their same address space at the same location.
So to see this, you'd have to basically have two Vista systems.
Right.
If you looked at the DLL layout of process A on one Vista system and the same process on another one, that's when you're going to see the differences.
Exactly.
So we can't easily demo that here. The service infrastructure has had some very interesting security hardening improvements that basically are designed to mitigate exploits of Windows services and the data that they can affect or access on the system. One of the things that's been added is the notion of a service-specific security ID, or SID. As you know, in XP and Server 2003, there's many shared services living in instances of SPC hosts that are running under either local system or local service or the network service account. And while that was a good step to take some of the services that ran with admin rights out, and there's more of that in Vista, there's an even finer grained way to have services locked down, and that is services are assigned a unique security ID when they're when the service control manager starts. Objects then that service is going to be accessing can have in their discretionary access control list the service-specific SID. So in other words, this object or this file, this directory, this resource can only be accessed by service A or service B. Now if we look inside the access token of a service host on the system, for example, let's pick this one. I'm going to the Security tab in Process Explorer, and we scroll down. we see these service-specific SIDs in the list. These SIDs represent individual services, and in fact, they're marked disabled in the token until the service starts. And those service SIDs can be applied to objects that the service might reference. Going a step beyond that is the option to mark a service as write-restricted, which means that the process can only reference objects that allow write access to that particular service SID. The former option allows objects to be protected to be only accessible from a given service, but this one goes a step further and says, all right, this service process can only get to the things that it's supposed to get to, so that if it's compromised, it's not going to be able to be used to access other objects in the system that it shouldn't access.
Another security footprint limiter in Windows Vista is the ability of services to specify what privileges they require to run. Privileges being things like shut down the machine, elevate their process priority up into the real-time range, things that could be dangerous and compromise not only that process, but the entire machine. They do that by specifying in a registry value called required privileges, the privileges that they actually need. And at startup time, the service control manager will go and look at those privileges, and when it creates the security token for that process that the service is running in, only place in that token the privileges that the service has specified it needs. If there's more than one service that goes in the same process, it computes the union of those privileges and stores those in that token. And you can actually see the privileges that have been assigned or been requested by a particular service by using the SC command with the new qprivs modifier option. And I'm going to look at the UPnP host service, and you can see that it requests several privileges, including SC change notify, create global, and impersonate. And if we went and looked at the token of the process in which it's running in right now, we'd see that it has at least those three, and maybe others from other services running in that.
We're at our last topic, UAC, formerly known as Lua. The goal of the UAC mechanism and infrastructure in Vista is to address the problem of we all run as administrators, right? But we don't really want to be administrators, but we need to be administrators, and there's apps that we know are poorly written that assume that they have rights to things that they shouldn't be messing with, like C Windows or C program files. This is something you can turn off easily. Of course, we don't recommend that. I know there's somebody in the audience who does do that. It's the first thing he does when he installs Vista. But like I said, Mark and I, we like the extra clicks. It gives us something to do. So what happens when you sign in? If you sign into an account like the one I'm logged into now, I'm going to bring up User Manager and just show you the properties of the account we're logged into. And now we see the elevation or consent dialog asking, do I give permission for this process to run with admin rights? If I look at the properties of this demo account, it is a member of the administrators group. However, if I go to look at the access token for the Explorer process, which was created at login time, we'll notice that the administrator SID in the token is marked as a deny SID, which means it can only be used to deny me access to things and not grant me access to things. Also, if we look at the bottom part of the display, the privilege list is vastly shorter than the normal privilege list for the administrator account. This is a limited token. This is not the token that, according to the configuration that I just looked at, I should have. So where is that token? It also was created at login time, and that's the token assigned to an elevated process. So if we go look at the token of the user manager process that I open, that's the mmc.exe, there's the administrator group in its normal state that we would see on an XP box. It's enabled, it's not marked deny. So he really does have admin capabilities. How can an executable request elevation? In the manifest file, or in the systems ActImpat database, or Windows for the common known setup exes will heuristically detect, yes, this is something that needs elevation, or you ask for elevation by doing right-click, run as administrator. Now that's a little confusing, maybe. It used to be called run elevated in the GUI. So run as administrator doesn't mean run this under the administrator account. It means run this under my account with the administrator SID in my token, not disabled, and the full privilege list that I would have had had I gotten everything that administrators are normally configured to get. Got that?
Got it.
Okay.
So let's talk about what goes on underneath the hood to implement UAC. There's a new concept, a new layer on the security model called integrity levels that's been added. And each process in the system runs at a particular integrity level. There's 4 currently defined integrity levels you can see ranging from low to system. And there's an example of a process that runs its low is the new protected mode IE runs at the very lowest integrity level. Standard processes, limited user account ones like the Explorer that we just saw, would run at medium. The ones that we elevate run at a high integrity level, and finally, certain system processes run at system integrity level. In addition, there's an integrity level on each object in the system. So every process and thread and token has an explicitly defined integrity level which reflects the integrity level of the process that it's associated with. Files and registry keys and other objects like that don't necessarily have to have an explicit integrity level, and if they don't have an integrity level specified for them, they're assumed to be at medium integrity level. So you don't have to waste your time assigning integrity levels to all of them or taking up disk space for those integrity levels. The integrity level assigned to an object, if it's being created by a process running at medium or higher, medium, high, or system, will be medium. And if it's created by something running at low, like protected mode IE, it will be defined as a low integrity level. Now, how do those integrity levels work with the access check? Before the standard Windows security access check even occurs, this new integrity level access check takes place. And the way this works is that a thread can only open an object for write access if that thread's integrity level is equal to or higher than that of the object. So something running at medium can only modify medium and low objects, for example. A thread can actually open any object for read access, though, if it's a non-process object. So even a medium thread could open an object marked as high, but unless that object is a process or a thread or a token. In that case, the integrity level of that thread that's doing the open has to be equal to or higher than that process integrity level. And that prevents protected mode IE from being able to mess with the other processes running at medium on your desktop.
Even just to read their memory spaces.
Even to read their memory spaces. And if protected mode IE is compromised, it can't go reaching in and trying to pull out passwords out of other processes running on your desktop. The Windows subsystem also honors integrity level. Dave mentioned the shatter attack that was prevented by the session 0 isolation. Windows Vista uses the integrity levels in the Windows subsystem by not allowing threads to send certain modification messages to Windows owned by threads running at a higher integrity level. And that prevents a process from going and performing a shatter attack against another process running on the same desktop that has been elevated. So when Dave hasn't created that elevated window, one of the medium windows on his desktop, it was a piece of malware, couldn't send Windows messages into it that would cause it to execute code or buffer overflow and then compromise that elevated process.
Now, part of making all this work involved dealing with apps that, as we mentioned before, assume that they have admin rights because they're trying to write to either parts of the file system or the registry that only administrators should have write access to. That all works because of UAC virtualization, which is done at two places. For file system, a new file system filter driver, Lua fv.sys, and in case of the registry, it's built into the registry code in the kernel. There are 3 locations in the file system that may be virtualized for a process that thinks it needs to write there. Program files, Windows and Windows System 32, and in the registry, it's HP local machine software.
So let's talk about what happens with the modifications that these apps that are being virtualized, where they go. If they make an app to one of those special locations and an override doesn't occur, and that location's in the file system, it gets written to a directory called app data local virtual store in the user's profile. If it's in the registry, it gets written to their registry profile under software classes virtual store. Reads that those applications perform, the system first checks the global location, or sorry, the per area location is attempted first, and if nothing's found there, then it'll fall back on looking at the global location.
Can you demo this, Mark?
And let's take a look at this. What I'm going to do is open up Process Explorer.
Which is running elevated.
Which is running elevated.
So it's not getting virtualized,
yeah, actually,
or it is?
It is. But I want to, let me make a version of this that's not running elevated. Window key R. C.
We have single instancing. We need to exit this first.
Okay.
Close. Okay.
Actually.
And can you add the virtualization column so that we can see?
We could, but we wouldn't be able to see everything because this is now running at medium.
But we can see ourselves as virtualized.
We could. So here we go. There's a new virtualization column, and it's actually in Task Manager as well as Process Explorer. And you can see that some of the applications, some of the processes running in my session are virtualized. Most of them aren't, as Dave explained. The ones that are built into Windows typically are not. But this Process Explorer is virtualized. And what I'm going to do is run FileMon, and we'll be able to watch
So let's just save the file.
Let's save the
We're
file,
not going to
okay.
have time.
So I'm going to save a file, and I'm going to try to save it to the Windows System 32 directory.
You're not supposed to write in there, Mark.
Actually, just window. I'll call it test.txt.
Wow, that worked.
And it looked like it worked, even though this thing is running at medium. So let's go look at Windows. And there's no test.txt there.
Where is it, Mark?
But there is under Virtual Store.
Oh, of course,
and
I would have thought
Windows,
to look there.
and there it is, under test.txt.
Unbelievable.
There's some interesting side effects, though, that might end up biting you when it comes to this virtual store, because a lot of apps on your desktop won't be running with virtualization, and some of them will, and you can see the kinds of behaviors that you might encounter when those two collide with each other. I'm going to navigate to C Windows and search for my test.txt, and there it is. I'm going to right-click and say Open with Notepad. Notepad is not virtualized, so it didn't find the test.txt in the Windows directory, and whereas the Process Explorer sees it because it is. So that's an example of an app compat potential issue you should be aware of.
Well, it's 4:30. We've covered a lot of ground in a short time. Again, there's a lot of things that we didn't cover, a lot of exciting changes in the Windows Vista kernel covered in sessions later on in the conference. The best place, wait, just give us a second here. The best place to look for more information is a paper that's been updated recently and is going to get updated again called the Kernel Enhancements for Windows Vista and Windows Server Longhorn. That is until Mark and I rev our book. And also, if you'd like to talk with us, we'll stay around after the session. We're doing a book signing at 7, and there's a list of the other sessions where Mark and I are speaking the rest of the week. Thanks for coming.